homework question. So we're integrating t squared sine 2t dt from 0 to 6 pi. Right? So a problem like this, let's see, what do we do? I think we had a problem like this. Let me quickly look at my notes. So, I'll be surprised at how quickly I forget those things too. Not sure where that example we did before. Yeah, we're going to have to integrate by parts. I think, so here by just looking at it, there are two functions that multiply together, t squared and then sine 2t. If you recall, we had an example, if we have integrating x to a power, let's say m of f of x dx, we usually let u to be the x to the m part, and then you can find du from there, and then we're going to let dv equals f of x dx. That's just usually that's an easy part. So here I'm going to do the same thing. So I'm going to let u just treat t as x squared. So I'm going to let u equals t squared. The remaining part, dv, I'm going to call it sine 2t dt. Obviously, you have to be careful because you have a sine 2t there, right? When you integrate that part to find v, you have to be a little bit more careful. V equals integral sine 2t dt. And then that, you might want to use a u-substitution to replace 2t. But I'm going to just do it directly, but check my work later. So if we integrate sine 2t, we get negative 1/2 cosine 2t. You can double check by taking the derivative. So that's cosine give you negative sine, and then 2t give you 2, so it comes out with 1/2. But anyway, so double check this part. And then du is equal to 2t dt. And then integration by parts formula says if we integrate from u dv, that equals uv minus integral v du. So now we're going to plug in those parts. The integral that we were given, that will become u, which is t squared, du is 2t dt, and then v is 1/2 cosine 2t, and the dv we already had at the beginning. So that will give us t squared times negative 1/2, so that's a negative 1/2 t squared cosine 2t. And remember that t is from 0 to 6 pi, minus integrating v. V is negative 1/2, so I'm going to bring negative 1/2 in front, put it in front of the integral. And then cosine 2t, and we still have du, which is 2t dt. Again, we can bring 2 in front of the integral, multiply with 1/2, and then the 2 negative become positive. So we get negative 1/2 t squared cosine 2t, evaluated from 0 to 6 pi. Minus minus is positive. 1/2 times the 2 that we bring from the 2 from 2t, bring it in front, that becomes 1, so we get positive 1. Just positive sine integral cosine 2t, and then we still have a t as well as dt. So this, if you compare to what I got in the integral here, so this integral, the integrand, the cosine 2t dt, it's very similar to what we had before, except that instead of having a a t squared, we now just have 1t, which is nice. Cosine and the sine, they're sort of the same, so you don't have to distinguish them. So we reduce the power of t by 1. And we still have t's going from 0 to 6 pi. And then the first part, you can evaluate that easily. The integral, you can focus on that by repeating the same process. So I'm not going to finish it, but I'm just saying that if you look at this, you can set u, just like we did setting u equals t squared. So here we're going to set u equals t, and then you can find dv, you can find v, you can find du, and finish it from here. So I'll let you finish it later. It's basically the same process, just to focus on this this integral part. And then you can solve it. So don't forget to evaluate this part directly. I hope that's helpful. Let me know if you have more questions on this part. Right. So this is good. I'm glad that you start working on the homework already. If you have not worked on the homework yet, definitely spend some time tonight, tomorrow, or Wednesday morning and afternoon to work on it. Because we don't have a review session before the exam, so go back to the exam part. Let me just say a few words. So we have a exam on Thursday that will cover 5.3 to 5.5, 6.1 to 6.3, 7.1 to 7.2. That's what's going to cover on the exam. And then we're going to finish 7.2 today. So 7.3 material will not be on it, but we're going to, we're not going to stop. We're just going to continue. Correct. So that's just going to be during class time. So on Thursday, we're going to spend half an hour at the beginning to answer any final questions you might have. Do like a sort of a quick review if you have any final questions. And then I'm going to give you about 1 hour and a half, so 90 minutes to work on the exam. So that will be from 6, 10, 6, so probably from 6:30-ish to 8. So that will be the exam time. And then you have another 10 minutes to upload your work. So plus 10 minutes to upload. So everything should be done by 8:10, unless you have extended time for accommodation. How many questions will be on it? So I don't know how many questions because I have not seen the exam yet. This has not been made yet. So I would say probably going to be so a quiz. We had what, 3 questions, 4 questions on previous quizzes. So I'll say maybe double that. So 6 questions at least. So 6, maybe 7 or 8 questions. So double the amount of quiz time. Anyway, so that's the exam. Any other questions on exam? We don't have extended time to review, so it'll be really nice that you look through the homework questions for this week before Wednesday lecture. Also review the previous quizzes and the previous homework questions, lecture, exercises from lectures. Review those and to bring any questions to lecture on Wednesday that we can spend a little bit more time on it. All right, so that's the exam, and that's the exam.
Will we be learning new content on Wednesday?
Correct. So we're just going to continue to learn the new content on today and on Wednesday. But if you, like I said, if you have questions about when you review for the exam, you should use the lecture time to ask them. How many questions will be on area and the curve? Any idea? I don't know. 2 questions maximum, I think. 1 or maybe 2. There will be definitely questions on volume as well. All right. Any other questions about homework or just in general questions before we move on? All right, so that's the exam. I'll put this information on the website as well, just so that you know. So last time we talked about how to integrate functions like, so recall, if we have sine to the mx cosine to the nx dx. So it depends on the power of m and of sine and the cosine. We have different approaches to rewrite this integral using trig identity. So here's a similar set of questions. If we have integral tangent to the m power x secant to the n power x dx. So there's a few cases. So case 1, if power of secant and if secant is even, so if that's the case, then save 1 secant square x. So that's what we need to save. We need to save a secant square x, not just secant, we have to save a square. And use the identity, also u-substitution. Use u-substitution, u equals tangent x, and identity, I believe, is secant square x equals 1 plus tangent square x. Check. Okay, that's correct. So that's what we're going to do. I'm going to use this example 1 here to show you if the process is similar to what we have done before, really not much different. So here, if you look at the example, the tangent to the 6th power, let's just put that aside, don't worry too much about it. Let's just focus on the secant part. The secant has a power of 4, so that's even. So this is even power. So that means we're going to save 1 secant square x. So we're going to take secant square x, put it aside. If we do that, I can rewrite the integral as integrating tangent to the 6x times secant square x times another secant square x dx. So this second secant square x, I'm saving it and for later. So this is what I'm saving. And then there's the secant squared, the first secant square. We don't need that. So let's rewrite that in terms of tangent by using the identity. So this integral becomes tangent to the 6th power x times 1 plus tangent square x. And then outside we still had a secant square x dx. Right. So far we saved the secant square. We rewrite the other secant square using the identity. And then the next, we're just going to use u-substitution. So we're going to let u equals tangent x du. If you recall, the derivative of tangent is secant squared. That's a benefit dx. And if you can see that immediately I have a secant squared x dx. And that it's the same thing as the sort of the ending terms in the integral, they're identical, so I can substitute that highlighted term with du as I replace tangent with u. So now the integral becomes integrating tangent to the 6 is a u to the 6. And the 1 plus tangent squared, that's 1 plus u squared. And the secant square x dx, that becomes du. So this goes there. That's du. Now I can continue to integrate. So that will be, we're integrating u to the 6 plus u to the 8 du. And the rest should fall pretty easily based on what we know using the inverse power, the power rule. So that's a u to the 7s, 1, 7, and then plus a u to the 9s, 1, 9, and then plus a constant c. The last step is to replace a u, which is tangent x, so 1 7th tangent x to the 7th power plus 1 9th tangent x to the 9th power plus a c. Any questions on this example? This case is very similar to what we did last time with cosine. You know, if the power of cosine is odd, we have to save a cosine and set u equals sine. If the power of sine is odd, we have to save a sine and set u equals cosine. Right, same thing. So this is this case. Now here's the second case. I think I'm going to have to put it on the side. But for you, you can, in your notebook, you can put them together with the first case. So the second case, in the integral of tangent to the mx cos secant to the nx dx. So if we have power of tangent x is odd, the power of tangent is odd, then we're going to save one. I mean, obviously we're going to have, let me add this, and power of secant is greater or equal to 1. So if we have this case, we're going to save 1 tangent x secant x term. So we're going to save a expression that's tangent x times secant x. So we're just going to save it, and then we're going to we're going to use u-substitution. U equals secant x in this case, and the identity that we're going to use is tangent x squared is equal to secant square x minus 1. It's basically the same thing as the identity above. We're just going to move the 1 to the left to give you secant square x minus 1 equals tangent square x. It's the same identity, just a different way of writing the equation. And here I have another example that I'm going to go over that with you after you write down the notes. This example I have here, I have tangent to the 5th power, so that's odd. And the secant to the 8th power, that's even, right? So wait for the telephone to stop ringing.
Call from Cambridge, MA. Call from Cambridge, MA.
So the power of tangent is odd. So that tells me that, okay, that's good. So let's start with practicing this trick there. So we're going to put one tangent and the one secant aside and to focus on the rest. So that becomes tangent to the fourth power x, secant to the seventh power x, and then aside I put away tangent times secant. So tangent x, secant x dx. Right, so just saving. So this is the part that I'm saving. So that's so save one tangent x times secant x. So the next thing is I'm going to rewrite the tangent to the fourth power in terms of secant. So first of all, I'm going to rewrite it as tangent squared. That way I can substitute for that tangent squared, and then secant to the seventh power x, tangent x, secant x dx. So that will become integrating tangent squared, so that's just secant square x minus 1 squared, secant to the seventh power x, we already had that, and then tangent x, secant x dx. You probably wonder, what's the benefit of having tangent x, secant x? Well, if you recall that the derivative of secant is tangent times secant. So that's exactly the next step is using the u substitution. So we're going to let u equals secant x du equals tangent x times secant x dx. This is really, really nice because that part and this part in the integral, they're exactly the same. So we can substitute that part with du. So the next step is just rewriting the integral using u and the du. So that's integrating u squared minus 1 squared u to the seventh power du. This is really good, right? Because we get something squared times u to the seventh power. You can expand the square, multiply with u to the seventh. The rest should be sort of straightforward in some sense. So expand the square. So that's now I want to point out that when you I don't know if you remember this from algebra class in the past. So if you have a plus b squared or a minus b, doesn't really matter. If you have this case, if you square that, that becomes a squared plus or minus, depends on the sign in the parentheses, plus minus 2 times a times b plus b squared. So that's just the rules that people come up with after they actually expanded a plus b times a plus b. So if you follow this two product, you're going to end up with this 3-term expression. You can either memorize it or just be careful when you expand it. So here, if I follow that formula, or if I follow this first term, so I get u to the fourth power minus 2 times u squared times 1, that's 2u squared, plus a 1, it's always plus there, times u to the 7 du. And then that will be, excuse me, multiply with u to the 7th, that's a u to the 4th times u to the 7th, that's a u to the 11th power, minus 2u to the 9th, plus u 7th du. And I'm going to let you finish this problem. It's really just find the antiderivative of each term and then put back u is secant x. I hope that's okay at this point. Any questions about those two techniques, that those two special cases with tangent and a secant? So one is that if you have the power of secant is even, you're going to put away a secant square because that's a derivative of tangent squared. That's in the derivative of tangent squared. If you have the power of tangent is odd, and then you have a secant somewhere next to it, you're going to put away tangent x times secant x, because that's the derivative of secant. Now you probably wonder next, what if you know, we don't have the either case. What if the power of tangent is even and the power of secant is odd? You can't follow either of this special case. Well, if that's the case, you just kind of have to work with it your best, because it's not that straightforward. But the basic idea is that you want to try to rewrite the expression, the integrand, with tangent squared or secant squared. So try with identities. Secant squared x equals 1 plus tangent square x, or tangent square x equals secant square x minus 1. Try with this. Maybe that may be helpful. Or may not be helpful. We'll see. For example, the first example, the 3 here, the power of tangent is odd. It's even. And then we don't have a secant term, so the power of secant is 0, right? So what we're going to do is that we can rewrite this as tangent square x times a tangent square x dx. And then the next step, you probably think like, can I replace both of them with secant squared? You can try that. There's that should be okay, because so you can write like this, or you can write as, let me use a different color. You can write as tangent square x squared dx. I haven't done that yet, so I don't think it's wrong. It should be manageable, because that will just give you secant squared, which is the even power of secant, which is good. So try that. That might be the easier case, but here, just follow this trend. So what I'm going to do is that I'm going to rewrite the first tangent square as secant square x minus 1. So that will be secant square x minus 1 times tangent square x dx. Then I'm going to distribute the tangent square in there. So that's secant square times tangent square. So I'm going to write as tangent square x, secant square x minus tangent squared x dx. The first term, it's not that difficult if you were to integrate tangent square x secant square x dx, because this term is a derivative of tangent x, right? So you could let u equals tangent x and then carry out the integration. But the second term, you're integrating tangent square x dx, that might be a little bit difficult. You might have to do something about that part, which again, it's we're going to use a secant square x minus 1 put in there. So the next step, let me see, how should I write this? I'm going to say the first integral, we're going to use u-substitution by letting u equals tangent x du equals secant square x dx. That's just for the first integral there. The first integral we can write as u squared and then du, because this is the derivative of tangent. And then minus the second term, I'm going to replace the tangent square with secant square x minus 1. So that's integrating secant square x minus 1 dx, which is not too bad, right? Because if you recall that when we integrate secant square, we get tangent x. When we integrate 1, we just get x. So it's not too bad. So just remember that's inside the parentheses. So that becomes, when we integrate u squared, that's a u cubed 1/3 minus, when we integrate secant square x, we get tangent x, but then we also integrating the -1, so that's a minus x. The last step is just rewrite the u. So that's 1/3 u cubed is tangent to the cubed minus tangent x plus a c. This is just the way that the book has. Follow this way. But like I said earlier, if you were to follow the part I wrote in purple there to substitute for tangent square there, you can just carry out by write it as secant square x minus 1 squared dx, and then expand the square, you get 3 terms, and then you can focus on integrating each one of them, because the first term has secant to the 4th power. How do we just know that the integrate of secant square x minus 1 is it's kind of a special based on the rule that to integrate this part, I basically integrate each term there. So I integrate the secant square x term to give me tangent. So that coming from, if you recall that the derivative of tangent x equals secant square x. So if we're integrating secant square x dx with respect to x, we should just end up with tangent x. So that's sort of the special derivative and integration rules there. I use that to get the derivative of this, the antiderivative of the secant square x, give me tangent. And then the -1, when I integrate just directly, that will give me minus x. Right? So like I said, if you try it differently, if you if you just expand that, you get 3 terms. You should be able to carry out with the integration of each term, because the first 2 has secant to the 4th, secant square, and then the -1 should be the same. Questions? Any other questions? All right, the next example I have is about tangent cubed. So here tangent is odd, but we don't have a secant term. So the good thing that the power is odd, but we don't have secant. If you recall earlier, we said if the power of tangent is odd, we're supposed to save a tangent x, secant x, put it aside to make it easy, right? That's for the power of tangent is odd. But here, the power of tangent is odd, but we don't have a secant, so we couldn't put away a tangent times secant without complicating the integration. So what we're going to try to do is that we're just going to try with the identity tangent square x equals secant square x minus 1. Let's just try with that identity and put in there, see what happens. So this integral I can rewrite as tangent square x times tangent x dx. And I'm going to rewrite the square with the identity. That's integrating secant square x minus 1 times tangent x dx. So that will be integrating secant square x. I'm going to put the tangent in front of it. So tangent x times secant square x minus integral of tangent x dx. just minus tangent x, and then we're integrating this dx. The first term, the tangent x secant square x, that's similar to what we had earlier, tangent square x secant square x dx, right? So we can use u substitution here. So let me rewrite this part. We can write as tangent x secant square x dx. That one we can use u substitution. The next integral is integrating tangent of x dx. So the u substitution here, we can let u equals tangent x du equals secant square x dx. Again, that's really nice because we have the secant square x dx there. So the first integral becomes integrating u du. I'm pretty sure all of you can integrate that part. How about the next one? How do we integrate tangent x dx? Well, that's a special rule, or if you forget about it, so I'm going to write down the special rule in a second, but if you just in case you forget this part, let me finish this, Chris, and I'll explain it. Just in case you forget how to integrate this, you can always write tangent as sine over cosine. So that's integrating sine x over cosine x dx. Now the sine is the derivative of cosine, cosine is the derivative of sine. Then you can let you use u substitution by letting u equals cosine x, and that should so du equals sine negative sine x dx, and then you can finish it from there. Right, so I'm not going to finish it. So that becomes integrating a negative du over u, which you can figure out. Now, Chris has a question. How do you know when to split the integral? Are you talking about splitting the integral in this part at the beginning when we split tangent cubed into tangent square and the tangent x? Because when I see this example, I'm thinking about there's no other shortcuts, right? So then I have to somehow get tangent square out of that so I can apply the identity. So that's telling me that I need squared.
I was talking about a few lines down where you put secant squared x in the box, that line, how you made two integrals.
Oh, okay. I see. This part, this line here, you can always do that because of the line above has a subtraction inside the integral. So whenever we have addition and the subtraction, we can always integrate each of them separately.
Would it not work if you integrated them together though? Like if you kept the tan inside the other integral?
You could integrate them together, but if you use u substitution there, it's not going to work because the second term complicates the problem. So if you say I'm going to let u equals 10, right? So let me just rewrite this to show you. So if I just keep everything all together, so remember I let u equals 10, du equals secant square x dx, so I can solve for dx. So dx equals 1 over secant square x du. So if I substitute into that line over here, into this line, so I get integrating u, and obviously I get secant square x minus u times dx, which is 1 over secant square x dx. So that will become, if I distribute the 1 over secant square, the first term is nice, it's just u left. But the second term, I still have u over secant square x dx. du, sorry. It's a du. So the first term is really nice. I get u du, but the second term, I have a x in the denominator, then I have a u in the numerator, which complicates the integration. So it's better just keep them separate.
Okay, thank you.
Yep, exactly. That's good. Well, what is the next step, right? Next step, in the second integral, you obviously the negative become positive, but you really end up with, so let me take this and then continue. So this line continues become integrating u du. I'm going to let you finish it, plus integrating 1 over u du. So if you recall that when you integrate 1 over u du, that's just natural log of absolute value of u. That's coming from here, plus a c. Which sort of this takes me to that the special rule with integrating tangent. So whenever we integrate the special rule, when we integrate tangent x dx, that's always going to be negative natural log of absolute value of tangent x plus a c. That coming from this process. I know there's a lot of errors going on. If you just memorize this special rule, so next time when you integrate tangent x dx, you can just use it directly. Let me make sure I wrote it down correctly. Oh, I did it wrong. Sorry, not which part did I not do it right? So tangent sine over cosine. So this cosine. I didn't write this down correctly. U is cosine, so negative natural log of cosine. That's why. You can rewrite this in the book. They use integrating tangent x dx is natural log of 1 over cos, absolute value 1 over cosine x plus c. That's just secant x. The equivalent, because it's a negative sign in front of the natural log, you can put it as an exponent. So basically you have a cosine x to the -1, and then that's a 1 over cosine x secant x. So they're the same. It's a negative because what happened here is that's a good point. But what happened is that I had a negative sign in front of the integral of tangent, which is this negative sign. But I combine with the negative coming from the integral, which is this negative sign. I sort of combine with that negative already, so you don't see that negative sign in the addition there. So it's minus a negative of this. So instead of plus, so that's a minus a negative of this, which is minus negative natural log. That's what that part is. That's the integral part. Good question. I just want you to see that from example 3 and 4, that even though you cannot use the tricks that directly, but you can always try to rewrite it, the given expression, rewrite it in terms of, like a sine, secant squared or tangent squared, and then replace them with Klieg identity and go from there. At least try that trick, and it will be okay. Any other questions on those examples? All right, the next part I went over it already. So this part I already went over this. If you don't remember, go back to the notes. This is the one you have a case that when you're integrating products of sine and a cosine, the power are 1, but inside they're different. So this identity that you can combine them, definitely check my notes from I think 2-3 lectures ago. maybe last Monday. Check that. All right, so that's 7.2. Any questions about those special trig integrals? At this point, we are learning new integration rules, like integration by parts, but we're also learning a lot of new tricks. With tricks, it's all about how to apply them in different cases. Obviously, it's a bit challenging for you to memorize all of them, right? But it is important and helpful if you do have them remembered. Or at least, when you say the question, you immediately know, oh, I got to look into this place, use this trick. At least know where you're looking for, where you're going to find the information to help you solve those questions. All right. Any questions before we move on? I'm going to start the next section, 7.3. Like I said, this will not be on this quiz, not on Thursday's quiz. Oh, sorry, Thursday's exam. But it is important for you to know it will be on the next assessment. So today we're going to focus on examples that specifically have a square root. And also in the square root, we get x squared, then we have a squared, we have the special cases. We're going to talk about how to integrate them. For example, if we have this integrating x over square root of x squared minus 4 in the denominator dx, we could just use u-substitution there to find the integral. So we can use, u-sub there. Or if we have x times square root of x squared, right, we can use u-substitution there. But if we have just 1 over square root of x squared minus 4 dx, we cannot use u-substitution. Well, we can try to do that, but then it's going to introduce a new term, which may be complicated to solve. So u-sub directly doesn't work. So direct u-sub may be complicated. Okay. So we're going to try a different kind of substitution. The first case, if you see examples with square root of x squared plus a squared in the denominator, or just in general square root of x squared plus a squared, and there's no other x somewhere else, or a squared plus x squared. So if you have this case, so what we're going to do is that we're going to let x equals tangent, so a times tangent theta. So we're going to introduce a new theta here. So this is what I like to do sometimes. When I see this expression have a square root of x squared, if I have this expression, what I do is I immediately draw a right triangle. I'm going to call this theta. And then I have a squared and x squared adding together. So that looks like, a squared plus b squared equals c squared, right? So I'm going to call the two sides of the triangle x and a, and that I specifically put x opposite from the angle theta. So if I have this setting, the hypotenuse here will be square root of x squared plus a squared, if you use Pythagorean theorem. That's sort of the triangle setup that I immediately think about that will be helpful to finish this problem. So if you just look at the drawing, and you can immediately tell that tangent theta equals x over a, and then you can solve for x from there. X equals a tangent theta. So that's what we're going to use. And then specific, so we're going to let x equals a tangent theta, and then specifically for theta is going to be, I'm going to look in the book because I don't have it remembered. I don't blame you if you don't remember all of those, but at least you should know how to use them. For theta is from negative pi over 2 to positive pi over 2. And use identity. 1 plus tangent squared secant squared x equals 1 plus tangent squared theta, I believe. So the rest is not important. The most important part is that we're going to let x equals a times tangent theta. That's the first thing you think about when you see square root of x squared plus a squared. And then the next case, if you have a subtraction, if you have a square root of x squared minus a squared, so if you have this square root in the integral, and immediately think about the triangle structure has theta here, because this is the x squared minus a squared. If you think about a squared plus b squared equals c squared, this is sort of like c squared minus a squared. So we're going to set x to be the hypotenuse. And this one we're going to call a, I believe. Check. So that means this leg here will be square root of x squared minus a squared. But I will see, memorize this. Let me use a different color there. So think about this setup. And from here, we can write as cosine theta equals a over x. And then we can write as secant theta equals x over a. And the x equals a times secant theta. So that's the substitution that we're going to use in this case. All right, bear with me. I know it's boring here, but kind of have to go through them quickly. Just 3 cases. For this case, the theta is from 0 to pi over 2, and all we can have theta that's from pi to 3 pi over 2. And then in this case, we're going to use identity secant tangent square theta equals secant square theta minus 1. All right, but that's just something to keep in mind, that every time you see square root of x squared minus a squared, think about the substitution x equals a times secant theta. The last part, if you have a squared minus x squared in a square root, and if you see that, I hope that you think about this triangle with theta here, with a being the hypotenuse, x being the opposite. So this leg here, the other leg is just a squared minus x squared. And from here, from the triangle, we can write sine theta equals x over a. Therefore, we can find out x equals a sine theta. So that's the substitution that we will use. This is for theta from negative pi over 2 to positive pi over 2. And then use identity. One minus cosine squared theta equals 1 minus sine squared theta. All right, I know that's like a lot about, probably nonsense to you now. Just 3 different cases, but what I want to emphasize is that when you, again, those are the three cases. If you have a square root of x squared and a squared, if they're adding, think about x equals a times tangent theta. If x squared minus a squared in the square root, think about x equals a times secant theta. And if you have a squared minus x squared in the root, think about x equals a times sine theta. I don't know if anyone know any shortcuts to memorize them. Feel free to let us know, but I don't know how any shortcuts to memorize them. But anyway, let me use some examples to sort of make sense of those cases. Like, why do we even, try this kind of substitution? What's the benefit of it? So the first example is the example that we didn't finish. If we have integrating 1 over square root of x squared minus 4 dx, how do we find the integral there? So let me take this example. That example, if we rewrite the full, so that will be integrating 1 over square root of x squared minus 2 squared dx, right? So that's like a x squared minus a squared. Oops. That's like a x squared minus a squared in the denominator case, right? So let me write, this is a case with square root of x squared minus a squared. Well, if we have this case, I believe it's the second case, right? X squared minus a squared. So if we have this case, so what I'm going to do is that I'm going to draw a triangle. I'm going to call this theta. And I'm going to label the hypotenuse x, the bottom leg a, and then this is become the other leg. A here is just 2, so we have square root of x squared minus 2 squared. All right, I'm going to close the window. It's out here. Anyway, so that's the triangle setup, and then the case 2 says we're going to immediately use the substitution. So we're going to let x equals a secant theta. So a is 2, so 2 secant theta. That's the substitution we will use for x. And then from there, remember, if you look at the integral, I have a dx, so I have to substitute for dx there. So I'm going to integrate both sides. So dx equals 2. Derivative of secant is just secant theta tangent theta. That's a special d theta. That's just a special derivative. And now we're going to substitute for the integrand. So before I do that, so I'm going to say x squared minus 2 squared just on the side. That's equal to x squared is 2 secant theta squared minus 2 squared. So that's a 2 squared. You can write a 4 if you like. Doesn't have to write as 2 squared. Secant squared theta minus 2 squared. Take out a 2 squared. So that's a 2 squared. Then we have secant squared theta minus 1. And as you can see that, if you recall that, why do I set that? Why do I set x equals 2 secant theta? So you can go back to the second case I wrote. That's if every time you say square root of x squared minus a squared, you can immediately think about, I'm going to use this specific substitution to make it easy, right? Or you could, if you set up the triangle like I did in this case, if you set up like x, it's a hypotenuse, 2 is a leg. From here, you can write as cosine theta equals 2 over x, but we want x equals something, right? So you can write as, just flip both sides. So that will give you secant theta equals x over 2, and then you can solve for x. So either way, you either kind of remember the substitution directly, or draw the correct triangle setup and then work out the substitution for x. Good question. So anyway, so here, let me finish this. So this part is just tangent square theta. So I get 2 square tangent square theta. It's really nice because that's a square, right? And if you remember in the integral, I have a square root of this. So that means square root of x squared minus 2 squared. That will just become square root of 2 squared tangent square theta. And that just becomes 2 absolute value of tangent theta. And in indefinite integral, we're always going to assume the absolute value part is positive. So we can just assume, assume tangent theta is positive, is greater or equal to 0 for, well, we know that happens when theta is between 0 and the pi over 2, and the theta is from pi to 3 pi over 2. That's why earlier we had those boundaries, those intervals for theta. But that's just to make sure that the absolute value part is positive. No problem, yeah, feel free to write full. Instead of 2 square, I just want to show you, really, there's no point, no specific meaning for me to write as 2 square. Absolutely, keep it as full. So anyway, so this part, we're just going to keep the positive. So we just take 2 tangent theta there. Now we can go back to the integral and rewrite it. So now that becomes 1 divided by square root of x squared minus 2 squared. After we've done all that, that becomes 2 tangent theta. And the dx, if you recall earlier, when after I set x equals 2 secant theta, I immediately took the derivative. So I get dx, I'm going to put it in there as well. So dx is 2 secant theta tangent theta d theta. And now I can simplify the 2, I can simplify tangent. So I end up with integrating just secant theta d theta. So that's what that's the benefit of using this kind of substitution by letting x equals 2 secant. We kind of get rid of the square root part altogether. And then we get rid of the square in the square root and just end up with like either secant, tangent, or sine, cosine, depends. So we end up with something trigonometric expression. Okay, and then we can integrate this from here. And this one, we're going to use a special rule. I'm not going to go through the work, but you can try to if you want to, by rewriting this as a 1 over cosine and use substitution from there. But I'm just going to use a special rule. I don't expect you to work out the process neither. So if we're integrating this, that just becomes natural log. I'm copying this from the book, by the way, this special rule. Natural log of secant theta plus tangent theta plus a c. So this is a special rule. And we're not done yet, almost. Well, we have one more step because the original function is given in terms of x, so we need to write in terms of x. Well, we have theta. How do we write it in terms of x? This is the part we need to use the triangle setup we had earlier. So recall the triangle setup I had was, this is theta, this is 2, this is x, this part is square root of x squared minus 4. So from here, what I'm going to do is I'm going to use the sides of the triangle to actually figure out what secant of theta is. So secant theta is 1 over cosine theta, And the cosine is adjacent over hypotenuse. So 1 over cosine is hypotenuse over adjacent, which is just hypotenuse is x, adjacent is 2. So that's x over 2. That's what secant theta is. And the tangent theta, you already know that's just opposite over adjacent. That's just square root of x squared minus 4 over 2. So now we're going to take those two expressions using the size of the right triangle and then put it back for secant theta and the tangent theta. So that's give me natural log absolute value x over 2 plus tangent is square root of x squared minus 4 over 2 absolute value plus a c. So this is my final answer for this for the integral that's given. This is the example that we have not done an example by following this kind of process before. This is the first time. So you basically you take the given function and then you rewrite the x using the angle theta and then use the right triangle. Then you sort of integrate it in terms of theta there. At the end, after you find it, you have to go back to the right triangle and then rewrite the theta in terms of x at the end. So you kind of like, you're translating the x variable into theta, and then you go back, rewrite the theta in terms of x at the end. This is called trigonometric substitution. Any questions on this?
Why is the base of the triangle 2?
That's just the setup. So every time, that's a good question, but this is, I did not come up with this rule. This is the rule, other people concluded, and then they find out this is this kind of setup is easy. So just like the beginning, so if you have square root of x squared minus 4, or like, you have square root of x squared minus 2 squared, that's a x squared minus a squared case. If you have that, you always want to set up the triangle so that the right triangle, so that the leg at the bottom is to the hypotenuse, it's x. And theta is the angle between them. That's just the setup they concluded. And then that will give you this leg, which is exactly the square root part, square root of x squared minus 2 squared. Square root of x squared minus 4. That's just that kind of setup that people, over the years have reached and found to be helpful. So that triangle setup is connected to the sort of the form of the square root part. That's why we go through all three different cases, because it depends on the form of the square root. You have a different setup for the sort of the sides of the right triangles. All right, let me go through. If you don't have any other questions, let me try to go through another example. Maybe that will kind of be a little bit more helpful in terms of understanding the process. So the next example I have, in the example, I have square root of 9 minus x squared in the denominator. So I'm going to rewrite as x squared over square root of 3 squared minus x squared dx. So this is like a square root of a squared minus x squared case. So let me write, this is the case of square root of a squared minus x squared, a being 3 here. And if we have this case, the triangle setup, A being the hypotenuse and X being the opposite. Just double check. I got confused too. Don't blame you. So X being the opposite leg. So that's corresponding to this case here. So if we have this, we can just by looking at it, we can see that sine theta is equal to X over A. Therefore, we can solve for X, which is A times sine theta. So that's sort of the substitution we're going to use. And in this case, A equals 3. So we're going to use, X equals 3 sine theta for substitution. And then we can solve for dx immediately. So that's a 3 cosine theta d theta. And then we're going to need those terms when we go back to the integral. But before I do that, let me figure out the last leg, the base leg of the right triangle. That's just square root of a squared minus x squared, which is, in this case, is 3 squared. Now I'm going to go back to the integral there. We're going to rewrite it, but before I do that, I'm going to find out 9 minus x squared first. So 9 minus x squared, that's a 9 minus x squared, so that's a 3 sine theta squared. That's a 9 minus 9 times sine squared. Take out a 9, so that's 9 times 1 minus sine squared. If you remember, 1 minus sine squared is cosine squared. You can write as 3 squared cosine squared if you like, or 9. Doesn't matter. And then we can take a square root of that, because in the given integral, we need a square root of 9 minus x squared. So that's a square root of 9 cosine squared theta. Take a square root of 9, which is 3, and the absolute value of cosine theta. Again, this is a indefinite integral. We're going to assume cosine is positive, which means to assume cosine theta is positive, greater or equal to 0, which means the angle theta has to be from negative pi over 2 to positive pi over 2. If you recall that cosine is the x value, so the angle from negative pi over 2 to positive pi over 2, everywhere between there, the cosine is positive or 0 in that right half of the circle. Right. So this part and this sort of equivalent. Why did I do the square root of them? Do you mean like the square root of 9 minus x squared? Oh, this part. So what I did is that I pick x to be, a sine theta, just because that's based on the square root. So I pick x equals 3 sine theta, and in the original integral, I have a square root of 9 minus x squared in the denominator. So what I did, I took 2 steps. I found out 9 minus x squared first. But that's not good enough, right? Because in the integral given, we have a square root of that 9 minus x squared. So I found out square root in the next step. So I can plug into directly without taking square root. So we assume cosine is positive, so we just get 3 cosine theta. So the next step is I want to take 3 cosine theta to replace the, why not just find the square root then? Oh, you could. You could just find I just take 2 steps. Are you talking about finding the square root of 9 minus x squared directly by putting x? If you talk about this kind of substitution directly, yes, you could just do that, and they should give you the same expression. I just took it as 2 steps. So either way is fine, right? I for some reason I just felt like I want to do it in 2 steps to make it clear, but absolutely 1 step is okay. Okay, so that's equivalent. So now we're just going to go back to rewrite that integral. This integral here. So that becomes integrating x squared, but recall that x is 3 sine theta, so they'll get 3 sine theta squared. That's the x squared in the numerator. The denominator, I get square root of 9 minus x squared, but we already found out that to be 3 cosine theta. And then don't forget that dx is 3 cosine theta d theta. Right? All of this seem to work out pretty well. So the next step is that we can let me add more space there. The next step is that we can just simplify a few terms. We can simplify the 3 cosine, which is really nice. Just end up with integrating the numerator, just give you 9 sine squared theta d theta. And in this part, I'm sure you remember from last time, you can integrate sine squared. I'd rewrite the sine squared. Well, let me just write down sine squared theta d theta. So if you have the power of sine is even, we're going to have to use the identity to rewrite it using sine squared theta equals 1/2 1 minus cosine 2 theta. We're going to use that identity to rewrite it, so we can integrate each term. So if I put in 1/2 1 minus cosine 2 theta, so I get 9 times integral 1/2 1 minus cosine 2 theta d theta. So bring the half in front and also integrate each of the terms separately. So that's 9/2 integrating 1 d theta minus integrating cosine 2 theta d theta. The 1 is just theta. Now the cosine 2 theta d theta, you can use u-substitution there, or you can just try to integrate directly but balance it with a constant in front of it. So if I integrate cosine, I get sine, so I'm going to write as sine 2 theta. But if I differentiate this, I get a 2 in front of it, so I need to cancel the 2, so I'm going to add a half. So this is sort of doing the this is basically doing the u substitution in my head, sort of, and then plus a c outside. Right? So the next step is finding theta, finding sine 2 theta using the triangle. So now we got the antiderivative in terms of theta. We have to rewrite it in terms of x. So recall that. So recall. Oops. So recall the triangle we had, which is right above there. So that's I'm just going to redraw it. So we get square root of 9 minus x squared. This is theta. This is x. This is 3. And then earlier we had x equals 3 sine theta. So remember that earlier we had x equals 3 sine theta. And here we need to know the theta. So I'm going to divide by 3. So I get x over 3 equals sine theta. And then if you remember that inverse trigonometry, that theta equals inverse sine of x over 3. So that's what the theta is. How about sine 2 theta? Sine 2 theta, of course, you might think, oh, can I just put theta in there? That's really not a good way to write it. So for sine 2 theta, we can write as 2 sine theta cosine theta based on the double angle formula. So that's 2 times sine theta, which we have. Sine theta is x over 3. You can also look at from here, or you can look at the triangle, the right triangle, right? And the cosine theta, again, we can look at the right triangle. We have all sides. So that's adjacent over hypotenuse. So that's a 9 minus x squared over 3. So that becomes 2 over 9x square root of 9 minus x squared. That's the sine 2 theta we can put in there. So the final answer is 9 over 2 theta is inverse sine of x over 3 minus 1/2 times the sine 2 theta, that's a 2 over 9. The 2 you can cancel. X square root of 9 minus x squared plus a 3. So that's at the end, after we get to this point, that's the final answer, because that's in terms of x. Whew. How are you guys doing there? Oh, to find theta there. So what I did is that it doesn't really matter. There's a few ways you can find theta. So what I did is I just kind of follow what we did earlier. Earlier we said the highlighted part x equals 3 sine theta, right? So what I did is I just take that, I divide by 3, and then take inverse sine on both sides. So I took this part and I divide by 3 on both sides. I get x over 3 equals sine theta. And then I just took inverse sine on both sides to find theta. You could also use cosine, or there's nothing wrong if you say, oh, can I use by looking at the triangle, can I write cosine theta equals x over, sorry, not cosine. Cosine theta equals square root of 9 minus x squared over 3, and then take the inverse cosine on both sides. Absolutely, that's totally fine. Inverse cosine of square root of 9 minus x squared over 3. That's okay too. So that's like a multiple expression for cosine for theta. It doesn't have to be just one. I just noticed that using sine is the easiest. Good question. Any other questions?
If you left the sine 2 theta and then just subbed in 2 times the arc sine of x over 3, would that work too?
Yeah, that would work. I wouldn't take points off, but we don't like just in general. We don't like to write something like or arc sine. It just mathematically, we don't like to write something like this, have a sine, then we have an inverse of a trig all together. We like to kind of like write it. This is considered not very simplified, because you have a inverse sine, then you have a sine outside. You might be able to rewrite it to simplify. So this is not a good way to leave it. So try to avoid write something like this if possible, using you know, the double angle formula or some other trig identity. Never mind. Okay. Why did it happen? Ah, yeah, that's being cancelled. Nope, it's still there. Okay. I really want to go through the next example. I know that you probably have a lot, but let me try to finish the next example, you know, in detail as well, just, you know, finish it, and then we can stop there. Okay, so that way you can, you know, process this tomorrow. I think I'm going to give you a homework just on this part tonight. It's again, you have like a 1 week to work on it. You know, I'm going to give you more time to, I'll probably make the deadline next Wednesday, but just in case you want to get ahead on this material, you can start working on it. Not a lot of problems. All right, so the next example I have, the denominator, I have a square root of x squared plus 16. So that's an addition of 2 squared. So here I'm going to rewrite as integral dx of 1 over x squared square root of x squared plus 4 squared dx. So this is a case of square root of x squared plus a squared, where a equals 4. Right, this is the sum of 2 squares in the square root. And in this kind of setup, we're going to draw the triangle with x on the opposite and the a being the adjacent. So in this setup, we can obviously solve for the hypotenuse. I'm going to do that later. But from here, we can just say, okay, tangent of theta equals x over a. Solve for x. So x equals a times tangent theta. So that's the substitution we're going to use for x. And in this example, a equals 4. So I'm going to put 4 here. So I'm going to use the substitution x equals 4 times tangent theta. And I can find out the hypotenuse, which is x squared plus 4 squared, 16. Which we're going to use that later at the very end. So I have x equals 4 tangent theta, and then I can find the derivative dx, which is 4 derivative of tangent is secant theta squared d theta, and I need that. And in the integral, I have a square root of x squared plus 4 squared. So or x square root of x squared plus 16. You can do it all together. So just like Sam said earlier, we can just say square root of x squared plus 16. That becomes square root of x squared. X squared is 4 squared, 4 tangent theta squared. So that's a 4 squared tangent squared plus 16. And then we can take out a 16 inside the root. So you get square root of 16. Tangent squared theta plus 1. And then that's secant squared. So square root of 16 secant squared. Take square root, so that's a 16. Sorry, that's a 4 secant theta absolute value. But again, we're only going to we're going to assume it's positive. So we basically assume that. So assume secant theta is positive, which means that the angle theta will be from negative pi over 2 to positive pi over 2. So secant is positive means the cosine has to be positive, right? Just like the previous case. So that's this half of the circle. So for any angle in that right half, cosine will be positive. Secant is also positive. Secant is 1 over cosine. So we just take the positive secant. So that's a 4 secant theta. now we're going to go to the integral we had earlier. So we had in the beginning, so that's becomes integrating 1 over x squared. So that's a 4 squared tangent square theta. That's x squared. And then we had a square root of x squared plus 4 squared. That's a 4 secant theta. And the dx, which is 4 secant square theta d theta. You don't like this. Those are not my favorite either, unfortunately. But we do have to, you know, those are like those important techniques that, or even just integration skills that we have to practice and to get comfortable with it, because later on when you learn something in a different class perhaps, or even later on, you have to practice this kind of techniques. Oh well, I hope you know your timetable well. Anyway, so let me finish this so I can let you go have some dinner. So I'm going to cancel the 4 and I'm going to simplify the secant from the secant squared. And that will give me integrating. I have secant theta in the numerator and I get 16 tangent square theta d theta. So what do we do from here? Well, from here, there's one thing that the book recommends, and also I think find it easy, is that we have secant in the numerator, tangent in the denominator. If we rewrite tangent square using secant square minus 1, we get something not nice as a fraction. So from here, it's easier just rewrite secant and the tangent in terms of sine over cosine. So just rewrite this, bring out this 1 over 16, bring it to the front, and then rewrite secant as 1 over cosine theta, and then the tangent squared, write it as sine squared over cosine squared, and a d theta. Rewrite this a couple more steps. So that becomes integrating. I'm just going to do it quickly so you can cancel out 1 of the cosine. That just gives you cosine theta over sine squared theta d theta. And we're almost done. I promise you, we're going to be done before 7:50. So from here, it's just all about finding the antiderivative by using, you know, anything that we know, right? We could see, we can let u equals sine theta because I see cosine theta d theta. So du equals cosine theta d theta. So I can put in there, this becomes 1 over 16, 1 over u, integrating 1 over u squared du. Whew, that's a 1 over 16, 1 over u squared. That's when we integrate 1 over u squared, that's a negative u to the negative 1, negative 1 over u plus a c. How does the 1 prove to sec? Sam, I'm not sure what you meant. In the middle, that was a 16 tangent theta. Oh, over here. Okay. So what I did, oh, I see. Good point. So over here, I took the secant. So from here, I rewrite it secant. It's just 1 over cosine theta. And then the 16 I brought it outside. So it becomes a 1 over 16 when I took it outside because it's in the denominator. And then the tangent square, I wrote it as sine. Tangent is sine over cosine, right? So tangent square is sine square over cosine squared. That's what I did. You say that. So I kind of rewrite where the square come from in the second of the last line. That's not a square root. I'm just underlining this integral. So I'm saying that this integral, if we focus on that by using u substitution and by letting u equal sine theta, that's okay. Those are good comments. And then I can rewrite it and end up with 1 over u squared du integrating. Sorry. Yeah, it would just underline. And let me quickly finish this. So that's a negative 1 over 16u plus c. And we can put back the u there, which is negative 1 over 16. U is sine theta plus the c. But this is still not good enough because the original function has a function of x, so I have to rewrite as sine theta. So if you recall that the triangle there, so from this triangle, we can find out sine theta, which is x over square root of x squared plus 16. And I can put it in there. So that's giving me negative 1 over 16. Denominator, I have sine theta, which is x over square root of x squared plus 16, plus a c on the side. Obviously, the next step is just rewrite the denominator, make it look nice. Calculus is so much. I have to say though, I know that's like a different path in calculus that could be, difficult to understand, but it's just techniques, right? Lots of techniques that they use. It's actually I don't know, overall as a subject, calculus 1, calculus 2, calculus 3. It's actually there's more fun stuff to it other than if you kind of look beyond those difficult moments. So that's a negative square root of x squared plus 16 over 16x plus a c. That's just after rewriting everything. All right, I'm going to stop there. 7:50.